this is Shiva. So this is another problem on coulombic force, right, between the charges, and this is another model. And yeah, let's see the problem. So a thin metallic wire having cross-sectional area of 10 to the power of minus 4 meters square is used to make a ring of radius 30 centimeters. A positive charge of 2 pi coulombs is uniformly distributed over ring, while another positive charge of 30 picocoulombs is kept at center of ring. Tension in ring is they've asked, provided there is no deformation in the ring. So it's a rigid one, right? So here's the ring, right? The radius is r. At the center, there is another charge, right? Point charge. So this is placed at the center. Due to this one, there will be coulombic force acting on each and every element of the ring, right? Of course, the total net force acting on Q due to the ring would be zero because it is placed at the center, right? And from all directions, there is force acting, and since it is symmetrical, right, all force components will cancel, and if there is no disturbance at all, this Q would be remaining there for all the time, right? Now, there is no disturbance or anything. There is just not a problem with HM. It is what they've asked us. Due to this one, what would be the tension developed in the ring? So obviously there would be tension because this is applying some force on the ring, right? Is a two-way one, right? Newton's third law, right? So if I consider some section of the ring, right, making so like if I consider this arc would subtend some angle. The semi angle I took it as theta, right? And I zoomed it. If I zoom this one, so this is Q, right? This is the section of the ring, and yeah, due to this one, at Coulomb force, right? Exactly, if I'm considering this length to be very small, so exactly in this direction I've considered my coulombic force. So due to this one, so tension would develop along the tangential direction in all the elements of the ring, right? So due to this one, the tension would develop at this last point. Tangentially, tension would develop. So in another tangentially, in another exactly opposite point, in the theta in the other direction, the same thing T would develop, right? So if I consider here this semi angle is theta, and if I take this another parallel line here, right, at exactly this point. So if this is theta, this would also be theta, and since this is tangent, right, this should be 90. If this is theta, this would be 90 minus theta, and again this is perpendicular to this one. So if this is 90 minus theta, this angle would be theta again, right? The same thing goes here also, right? And so if this is t cos theta is acting in this direction, and another t cos theta at exactly other end is acting in this direction, that is t cos theta, right? These two exactly cancelling out each other, right, for the given element, for the given symmetrical element, right, theta and theta. And t sine thetas, both t sine thetas are acting downwards, right? So if I equate these two, right, in equilibrium condition, fc t sine theta, t sine theta, so what I'm writing is 2t sine theta is equals to my coulombic force of repulsion, right, due to point charge on the section of the ring. That I'm equating it to two tension components which are acting downwards in the given section of the ring, right? So 2t sine theta is equals to coulombic force of repulsion, that is 1 by 4 pi epsilon naught q1, that is small q for this section, right? This section, since we know the r and r and theta, right, we'll get the length of this one. So length would be r theta, right? So and I've calculated dq, the small charge for this section of the element, right? That turns out to be q theta by pi. You can compute this, right? Lambda is equals to, that is linear charge density, right? Q by total charge by total length. that I've written in differential form dq by dl. From here dq is equals to q by 2 pi, dl goes that side. Dl, as I said, length of the arc is r theta, right? So if I r into the total, sorry, this is up to this angle is theta, the total angle would be 2 theta. So that I have substituted here, right? So I got small charge as q theta by pi. Okay, so now coulombic force of repulsion. So we know the distance and we know the elementary charges, point charges, k q1 q2 by r square. So 1 by 4 pi epsilon naught q. This charge is q theta by pi, right? Q theta by pi divided by the distance square. Sorry, this would be capital R square. Excuse me. Right. So the distance square, capital R square. So that I've written here, right? Now I should take this one small theta, right? The small angle. So if I consider small angle, so that would be sine theta. I can almost equate it to theta. So 2t is equals to this much, and t would be this much, right? So I got this expression, and 1 by 4 pi epsilon naught value I put 9 into 10 to the power of 9, and q value they're given 30 picocoulombs, that is small element charge which we have put at the middle, in the middle, right? 30 picocoulombs. Pico is 10 to the power of minus 12, right? Into capital Q. Capital Q, the total charge on the ring. Total charge on the ring is given as 2 pi. So that I've substituted here, right? And divided by 2 pi into r square. Radius of the ring. Radius of the ring is 30 centimeters. So that I've substituted here. And if I compute this, tension turns out to be 3 newtons. So I hope you got the point and what we've done here. So first we'll consider some section of the ring, and then took that tension acts always tangential. So this kind of same thing, um, if I see in first year, right? That is in the waves, right? In wave section, for if we give some energy, right? For example, if we give some pulse to a section of the rope, there also we kind of will see the same thing, right? The tension will develop tangentially on the rope while calculating intensity and pressure, etc. Not pressure, intensity and the energy of the wave, right? So basically whenever there is a fluidity, right? Not fluidity in the sense, whenever there is a force which is given to some object, it tends to distribute on the object. So I mean, uh, yeah. So that force, especially in this example, that tension turns out to be acting tangentially, right? Okay, so hope you understood. And yeah, this is going to be my final example on coulombic force between two charges. I hope I covered most of the models, covered some miscellaneous models and pyqs and NCRT exemplar. And from my perspective, these are some of the models that students would find most difficult. Topic would be electric field. So there also we'll see the same kind of miscellaneous and what I think that students would find difficult. And if you do find any other problem, excuse me, if you do find any other problem that you find difficult or anything otherwise, so please do comment. And yeah, thank you very much. I'll see you in the electric field in the next video.